Our last topic in this chapter is nucleophilic aromatic substitution. Nucleophilic aromatic substitution is fairly different from electrophilic aromatic substitution. It has two different shorthand names. You can call it SNAR, which mirrors the SN1, SN2 naming, or NAS for nucleophilic aromatic substitution, which mirrors our nickname for electrophilic aromatic substitution, EAS. So both of these shorthands are acceptable. Now, nucleophilic aromatic substitution uses a very different situation. Instead of creating an electrophile and allowing benzene to act as a nucleophile, the benzene is actually going to be an electrophile and will be attacked by a nucleophile. So our goal here would be to displace the chloro group with the hydroxide, although in this case, this reaction actually would not occur. The only hang-up for nucleophilic aromatic substitution is that you have to have electron withdrawing groups present on the benzene ring in order for the reaction to occur. This allows for less electron density to be present at the halogen carbon and make it more susceptible to substitution, i.e. we want to make this carbon more electrophilic, more attractive to a nucleophile. So for example, if we add on a single nitro group, as in the top example, we see direct substitution of the chlorine with the hydroxyl group. But note that this takes 130 degrees Celsius as our temperature. So some pressure, some heat has to be applied here. If we add on more nitro groups, one more, we can go to 100 degrees Celsius. And if we add on even another, we can go to just 35 degrees Celsius, which is barely above room temperature. And these reactions occur readily because the nitro groups are pulling electron density out of the benzene ring and increasing the positive nature of that carbon. Now let's take a look at the mechanism because it's not as straightforward as SN2, even though it looks like it should be. The mechanism for nucleophilic aromatic substitution is called an addition-elimination reaction. So in our first step of this mechanism, what we see is that the hydroxide group attacks the carbon that has the chlorine on it. And those electrons from the pi bond actually get pushed to our neighboring carbon. So we have added the hydroxyl group and pushed the electrons to the neighboring carbon. This intermediate actually has its own special name. It is known as the Meisenheimer intermediate. And this intermediate has several different resonance forms which help us to explain why the nitro groups help this reaction occur. In the first example of resonance, we can take these electrons, create a new pi bond, and push these electrons onto the carbon that has the nitro group. And it is important here to remember the structure of the nitro group. Remember that when you draw out the nitro group, one of the oxygens has a negative charge and the nitrogen is positively charged. Now we can take these electrons and actually push them into the nitro group by creating a double bond to the nitrogen and a single bond to the other oxygen. This structure can definitely help us see why the nitro group is electron withdrawing, because it is able to, by resonance, pull the negative charge into the nitro group. Now we can take these electrons and push them back through. And from this last resonance form, we can actually show that final elimination step, and we could have shown that from the first one as well. Here we're going to take these electrons, create a double bond, and kick out the chlorine to give us our final product, where our hydroxyl group has displaced our chlorine. But again, note that even though it looks like a direct substitution, just like with SN2 reactions, that's not actually what's happening here. We are attacking the carbon that has the halogen, as we saw in the first step, and then the pi electrons get pushed onto the neighboring carbon, and it's those electrons that actually push out the chlorine. So it's kind of like a tug of war with electrons. You push the electrons to one side, and they get pushed back the other way. In our next reaction, we're going to do nucleophilic aromatic substitution, but with a different nucleophile. Now, with SN1 and SN2, we saw that switching out the nucleophile did not have an effect on the mechanism. If it was going to be an SN2 reaction, it was going to stick with the same SN2 mechanism. However, that's not the same for nucleophilic aromatic substitution. Depending on your nucleophile, your mechanism could be very different. So in our first example, we have azonide, which is something that we've seen before. It is NH2, with 2 lone pairs on nitrogen and a negative charge. So we have a negative charge here and a positive charge from the potassium. Remember, the potassium is not something that we're super worried about here. Now, there's something different about azonide when you compare it to hydroxide, which is that azonide is a much, much, much stronger base. So notice that this reaction is actually happening at negative 33 degrees Celsius. So not only do we not need heat to initiate this reaction, we actually want to make it cold and slow the reaction down a little bit. So in this mechanism, since azonide is a much, much stronger base than hydroxide, it is going to do something very different as its first step. Instead of directly reacting at the carbon and adding, it's actually going to choose to pull a proton off of our compound instead. So we take this proton, and these electrons end up on that carbon. So we are simply deprotonating it. This allows us to actually take those electrons and create a triple bond and kick out bromine. Now you might be wondering, why don't I take the electrons and put them this way? Well, if you do that, you're creating a double bond here, which is going to create a 5 bonded carbon monstrosity that we are not going to draw in this class. But by creating a triple bond and kicking out bromine, you create a very interesting species known as benzyne. So for just a second, think, does benzyne look like something that is stable? Does it look like something that's going to wait around for a reaction to occur? Hopefully you said no. You know that alkynes like to be linear, and we're forcing this one to have the same geometry as the sp2 carbon that it came from. So this compound is highly unstable and also highly reactive. So now we have this benzyne, and we have even more of our azonide around, and it's going to be able to attack either one of the carbons. It could attack the top carbon, or it could attack the carbon where the bromine came from, and then those electrons get pushed back onto the carbon they came from. So that all we have to do from here is pick up a hydrogen from the equivalent of ammonia that we made in our first step. So that we end up with aniline. Now you may be wondering, how do we know that it goes through this crazy benzyne intermediate? If it's so unstable, why would it even form? So the ways that we know are that we can run different tests. So in this first example, we have taken chlorobenzene, and the carbon that has the halogen on it has been radio-labeled using carbon-13. So that asterisk indicates to us that is a carbon-13 atom, which we could track through carbon-13 NMR. Now we react it with potassium azonide, and after that first elimination step, we end up with benzyne. From here, our compound is going to react with further azonide and ammonia, to give us our product. But the question is, where does the amino group of aniline end up? Does it end up on the radio-labeled carbon, or does it end up on the neighboring carbon? What you would find if you actually ran this experiment was that you get a pretty even split of the two products. So this tells us that once the benzyne has formed, neither of these carbons is any different from the other. And so we know that something like benzyne must form, otherwise we would see so much more substitution directly at the radiolabeled carbon if we were seeing just a direct substitution of azonide with chlorine. But because we end up with a mix of products, we know that's not the case. Now, another example to help us, deal with this concept is that if you take a di-substituted benzene derivative, note the trifluoromethyl group is electron withdrawing and therefore really, really good for nucleophilic aromatic substitution, we actually end up with a rather surprising product. If we were to expect azonide to directly displace the chlorine, we would expect to get either, only the ortho product or majority ortho product. But what we actually see is something very different. We end up seeing the meta product only. Now, the only way that this could occur would be if benzyne were formed and then the azonide group were able to add to the opposite carbon. Now, one more. If you were to run a reaction like this with azonide and insert furan at the correct point, this is furan, what you find is actually a Diels-Alder adduct between benzyne and furan. And again, the only way that this could occur would be if benzyne were formed at some point in the reaction. Now, our last pair of reactions for the chapter, I know I said nucleophilic aromatic substitution was last, but this is one slide, just real quick. We're just looking at some quick reductions of aromatic compounds. So the first thing that I want you to note is that you can use your generic hydrogen gas and transition metal combination that you use with alkenes, but it's going to be very, very slow. You can remove one of the double bonds from benzene to end up with a mix of products. You're going to end up with the 1,4 and the 1,3 cyclohexadiene. And then if you add in your same hydrogen gas and transition metal, you're going to very quickly get rid of one of your double bonds to give you cyclohexene. And then you can further remove that one by adding in the same hydrogen gas and transition metal to get you cyclohexane. So that is one way to reduce an aromatic compound. However, it's going to take probably a lot of heat and pressure if you actually want to see that first step ever occur. So another way to do this would be to use the Birch reduction. So the Birch reduction is a very specific set of reagents. You're going to use either sodium or lithium metal. Notice these are not ions. And you use ammonia. You might also see it written out as liquid ammonia. That just indicates that it's concentrated. And ethanol. And what you get from this is explicitly the 1,4 cyclohexadiene. Now, the reason this is important is that this reaction happens much more quickly, and you don't have to worry about using hydrogen gas, which can actually be fairly dangerous because it's flammable. So if you wanted to heat it up under pressure, that's kind of a bold choice, which is what you would potentially have to do for this first step. So the Birch reduction can actually help you get around those dangerous conditions. However, sodium metal is not particularly safe either, especially in the presence of ethanol. Now, another cool thing that can happen with the Birch reduction is that if you do the reduction on a derivative such as anisole, you're still going to get the 1,4 cyclohexadiene. Note where the methoxy group is. It's not in between the double bonds. It's actually on one of the double bonds. And then if you further work this up with aqueous acid, you end up with kind of a weird reaction where you end up with a conjugated system. This is called an alpha-beta unsaturated carbonyl compound. So anyway, the Birch reduction is really neat. This is an example that you can almost certainly expect to see, a single quiz question or a single exam question. This first step is very usable in a lot of different ways, especially synthesis problems. So this is a valuable reduction to have in your mind, and definitely putting it on a flashcard would be a good idea.